This is the continuation of this video, Chapter 7, Section 6, Video 6. So if you haven't watched Part 1, you should go back and watch Part 1. All right, so let's quickly review what happened in steps 1 and 2. Summarizing, in step 1, we derived that 1 minus cosine of A is equal to that fraction, and 1 plus cosine of A is equal to that fraction, where A, B, and C are the sides of a triangle, and S is the semi-perimeter, half the sum of the sides. In step 2, we derived that cosine of A over 2 equals this square root, and sine of A over 2 equals that square root. Now we're on step 3, which is to incorporate the sine area formula. Remember, we're trying to find a formula for the area of a triangle in terms of its sides. Recall that the area of a triangle can be 1/2 BC sine of A. There were two other variations if you permute the variables, but that gives the area of the triangle. If we solve for sine of A, we get sine of A equals twice the area over B times C. Now, let's use the sine double angle formula. Sine of 2 theta equals 2 sine theta cosine theta, with theta equal to A over 2, and that'll give us sine of A equals 2 sine of A over 2 cosine of A over 2. Now, we've got expressions for all three of these trig functions. Sine of A is right here, sine of A over 2 is that, and cosine of A over 2 is this. So we're going to make all those substitutions. There's the comment that we know all these things, and we substitute those into this formula, and we get sine of A, which is this fraction on the left, equals 2, this 2 here, sine of A over 2, which is this first square root, cosine of A over 2, which is the second square root. Now, look at what we have at this juncture. We've got an equation that has 5 variables. 1 is the area of the triangle. 2, 3, and 4 are A, B, and C, the three sides of the triangle. And the fifth one is the semi-perimeter. So we've pretty much cracked the door open on what is the area of this triangle in terms of A, B, and C. I know it's also in terms of S, but that's also in terms of A, B, and C. All we have to do now is make this say A equals and try to make it pretty. So we're going to solve for A. Now, we're going to solve this pretty quickly by making some observations. Number 1, there's a 2 on both sides of the equation, so we could divide both sides by 2 and they would disappear. And number 2, look at the 2 square roots denominators. If we were to split each fraction into its own into a fraction of 2 square roots, we would have the square root of the numerator over the square root of the denominator. So we would have in both denominators the square root of BC times the square root of BC. But the square root of BC times the square root of BC is BC. So on the right side, the denominator simplifies into just BC, which is the same denominator on the left side. So if we multiply both sides by BC, the fractions would cancel. So the 2's are gone and all the denominators are gone. That leaves A equals the square root of all the stuff that's in the top, S minus B, S minus C, S and S minus A. We're going to put the S and the S minus A first, followed by the S minus B and the S minus C, and that would give us a formula that looks like this. Area is the square root of S times S minus A times S minus B times S minus C. This is called Heron's formula, sometimes Hero's formula. It expresses the area of a triangle in terms of the lengths of all three sides. Recall that the semi-perimeter is also in terms of the lengths of the three sides. And I'll pause the video just for a second because this formula deserves to have a highlighted box around it. All right, so all we got to do now is demonstrate how to use this formula, which is pretty straightforward except for a little bit of arithmetic. For example, find the area of triangle ABC. If A equals 12, B equals 16, and C equals 26, give the exact area and the area to the nearest tenth. Now, we should mention that we should check to make sure this is actually a triangle, because otherwise we'll get a nonsense answer. But checking the sum of the two shorter sides, 12 and 16, it does exceed the third side. So this does satisfy the triangle inequality. Now we're going to use Heron's formula. We first calculate the semi-perimeter, which is half the sum. And the sum divided by 2 is 27. So the area of the triangle is the square root of 27 times 27 minus 12 times 27 minus 16 times 27 minus 26. Let's push this as far as we can without rounding. We do all the subtraction problems first. 27 times 15 times 11 times 1. Multiply them all together. We get the square root of 4,455. Now, depending on your professor or your homework platform, you may be asked to simplify the square root. It does simplify by breaking it down into 81 times 55, and then the square root of 81 is 9. But knowing to break down 44,455 into 81 times 55 is a learnable skill, but it's not obvious what happened. We'll get back to that in a moment. Now, that's the exact answer. We could just put it into a calculator to get that the area is approximately 66.7. I'm going to make a third follow-up video to explain how to break down this square root pretty easily, especially in this flow. But for now, pause the video and try the following. Find the area of a triangle whose sides are lengths 8, 12, and 16. We're looking for the exact and the approximate. All right, if you haven't paused the video, here's your fair warning. Solution in 3, 2, and 1. The semi-perimeter ends up being 18. So the area is the square root of 18 times 18 minus 8 times 18 minus 12 times 18 minus 16, which is the square root of 2,160, which factors into 144 times 12, the square root of 144 times 15. The square root of 144 is 12. So the exact area is 12 times the square root of 15, which is approximately 46.5. Again, I'm going to do a follow-up video to talk about how to simplify these square roots because I kind of take that for granted. But in a context like this with large numbers, I think it's worth a video.